All right, welcome back, all. We have another fun filled lecture for our Math 32 class today. This topic is called estimators, and admittedly, it's another more theoretical setting that we should cover for the semester. My plan this week is today to cover the topic of estimators. Wednesday covered the topic of refining or optimizing estimators. And then finally on Friday, we'll hit the central limit theorem, one of the big topics of the course. And thus, in other words, what we're doing today and Wednesday is setting up Friday's lecture. Based on feedback we got last time, I thought what we should do is a more concrete example at first, just have some numbers to look at, and then we'll dive into the theory. So, at the beginning of the semester, I surveyed all of you and took down and gathered a bunch of data in what was called a demographic survey. And what I'm doing here is pretending that I took 5 observations, 5 data at a time. So here we have a list of heights. The units were inches. And as you can see, I gave them some notation, x11, x12, etc. And we're going to call T1 the average of those 5 numbers. Now, this semester, there were 300 students in this Math 32 class. In fact, I had about 450 students overall this semester. So let's just go ahead and assume that I did the same procedure over again. I sampled another 5 students and recorded their heights. And for this thought process, I went ahead and took the average again, T2 being the average of those relatively tall people. And just for the sake of argument, let's assume that I did this one more time. Took another sample of 5 people, recorded their heights, and then took the average of that sample's height. Or the average of that sample. So, what I want to emphasize at this particular moment down here is that the sample mean usually changes upon a new set of observations. That is, the sample mean itself is random in some sense. So, what I want you to do is just kind of stop for a minute and think about these inquiries I'm giving you right now. Can we calculate the average height of UC Merced students? And how can we calculate the average height of UC Merced students? Let's go ahead and think about that for a bit. It's cool. I just got an email asking for volunteers to help analyze data for COVID-19 patients. Maybe I'll look into that after class. So the people in chat are hitting this correctly. That based on what we've seen so far, perhaps the route will be to take an average of the averages to take a mean of the sample means. Good job. Now, I'm going to try to explain this concept of estimators in a fairly straightforward way, but just for a couple minutes here, just for the sake of rigor, I'm going to introduce some notation. So we're going to let capital T be a random variable and f, as usual, be some function, some calculation. These lowercase x's were the observations. In the previous example, these were student heights. And the way the definition, the main idea goes today is that if we are trying to estimate a population parameter labeled theta, we say that capital T is an unbiased estimator if the expected value of T still lines up with theta. And what I hope to do today for the rest of the hour is to try to walk us through what this means. What I mean by lowercase f is in the notions of statistics, we'll be looking at situations where f is calculating the mean, variance, and standard deviation of the observations. I'm just pausing to catch my breath, and also if people are actually taking notes that we did in face-to-face classes. While I'm here, I'll probably note that what I'm going to do is actually jump back and forth between this screen, what is called Overleaf, and LaTeX, and I'm going to jump back and forth with RStudio and the R code. The question in chat is, would a bias estimator be systematic shift? I'm not quite sure what you mean by systematic shift, but what a bias estimator would do is probably underestimate or overestimate what you're trying to do just from the sheer calculations itself. Yeah. All right. So what we're gonna do instead of looking at the student heights over and over again, we're gonna run simulations where the random variable is a uniform distribution between 0 and 1. And the reason why we're doing this is because we know what the answer should be. In particular, if we have a uniform distribution between 0 and 1, then the mean is right in the middle at 1/2. The question in chat is, since I suited up today, what do my pants look like? They're just sweatpants. All right, so here in RStudio, the first two sentences were the ones I just said above. As a task, the question is the sample mean, remember we called that x bar, an unbiased estimator of the population mean, mu? Like in some previous simulations might have shown you, I'm going to let capital N be the number of iterations or the number of samples. Here I set that to 10,000. I'm going to let lowercase n be the number of observations per sample. And just as a programming note, I'm going to let t sub capital N just be a vector to allocate to space first. Also, in R programming, I could not call this just plain capital letter T because that's reserved for the notion of true, as in true or false. Now, the for loop will do pretty much the same thing that we just did with the student heights. We're going to get random numbers. By default, they're between 0 and 1, and we're going to get lowercase n, 10 of them. That's what I call this sample. Then from there, I'm going to take the mean of this sample. And then finally, this third line of code in the for loop records this sample mean. And before I forget, for my Math 32 students, I have already uploaded the code to our Canvas page as well. So once again, if we're pulling these numbers from a uniform distribution between 0 and 1, we know that the population mean, the result is 1/2 or 0.5. If we take random numbers from that distribution 10 at a time, find the average each time, and then, like you said, take the average of the averages, what we're hoping to do in some sense is land right back on the 0.5. So once we run that simulation, we get a number down here that is arguably close, close in loosely speaking, to 0.5. And what we did empirically, this last paragraph I have at the bottom, is that since the mean of means seems to align with the true population mean, mu equals 0.5, our simulation implies that the sample mean x bar is an unbiased estimator of the population mean, mu. I'll pause here to take any more questions from chat. You know, questions are not trolling. Trolls are allowed as long as you're funny and not disrespectful. So the question in chat is, how are we interpreting unbiased estimator? So back in the student heights data, what we were doing is looking at samples of heights from our fellow students in this one classroom. And we were trying to guess the average height for all students at the university, but only using the data we had. What we just showed is that since the sample mean is an unbiased estimator, we could take a mean of means, and it seems to be a pretty reliable way to estimate the larger population, the average height of the larger population. So, yes, the point of the unbiased estimator is to try to get a result that's not skewed along the way to describe the larger population. And forgot that I had the sentence back here. The question in chat is then, what will a biased estimator look like? And we'll get to that in about 10 minutes. Now, what I did in RStudio, I will emphasize I did that empirically. It's just kind of hand wavy, the so-called proof by picture or proof by computer program, proof by example. This being a sophisticated math class, we should actually do a rigorous math proof every once in a while. So it's going to be a theorem or a fact that the sample mean is an unbiased estimator. To set up some more notation, we're going to let x sub I be a set of n IID random variables. Remember that IID means that the random variables are independent from each other and identical in their distribution. That is, the observations could still be different, but the distribution from which they came were the same. So we have the same distribution, meaning that each of the random variables, capital X, has the same population mean mu. And to show that such a situation, calculation, in this case the sample mean, is an unbiased estimator, we double check this definition, that the expected value of the sample mean points us right back to mu. Now, we've actually did this proof before, so I'm going to vomit it onto the PDF here. That is, we simply ran through the definition. The expected value of x bar was the expected value of how we find x bar in the first place, adding up all the capital X's, dividing by n. N is a constant with respect to the randomness, so we could factor out that constant. We had seen in previous classes that across plus signs we could split up the expectation operator. Because of the assumption that the xi's or iid was the same population mean mu, we have each one of these terms becomes mu. And because there are n terms, this is n mu. And finally, we're left with just plain mu at the end, which is what we wanted to show in the first place. The question in chat is, should we know how to do this proof? Especially the way that we are running the class here in this weird COVID-19 semester. The cynical answer is that you should know how to look up this proof should you be asked to do it. So finishing off the train of thought, since the expected value of x bar does line up back with mu in the theoretical derivation here, we conclude that the sample mean x bar is an unbiased estimator of the population mean mu. I'll pause here to see if there are any more math questions from chat. The question in chat is, how do we go through this process if we don't actually know the population statistic, in this case the population mean? The aspect of the math proof is that we want this to be able to still be true in a bunch of various situations. For example, in different distributions, whether we have the exponential distribution, the normal distribution, the gamma distribution, etc. So you'll notice that this proof, while we say that mu is the population mean, we never actually say what that number is, and we never even said what the distribution is. And thus, the reason why this proof holds in many situations is because we did not make those assumptions, and these calculations would still work in different situations. Question from chat is, how do we know that all the expected values are equal to mu? Admittedly, that was the assumption at the very beginning, that xi's are iid. Since they're identical, we said that each one of them had the same population mean mu. All right, apologies to the note takers, but we need to move along. Me being a math teacher, you could imagine that I wanted to show you a situation where something worked, and a situation where something does not work. And now we'll look at variance. Similar situation, x is a random variable distributed between 0 and 1. You could look up the formula for variance for a uniform distribution, and you would find that in this situation, our population variance is sigma squared equals 1 over 12. One over 12 is about, for our reference, about 0.0833. Now, what I mean by variance is, remember way back when I said that scientists wanted to get a sense of how spread apart the numbers are. They did not care if the deviations were positive or negative. So what we did was we took the data and we subtracted the mean from each observation, and then we squared the deviations. Now, to play devil's advocate, just to kind of go down this old train of thought, we're going to take these squared deviations and take the average of them. So we're going to add up all the squared deviations with this sum command, and we're going to simply divide by n for now to see how this all plays out. Otherwise, the for loop in the rest of the code is the same structure as the previous example. Now, again, all this sampling and then taking the average of the calculations should line back up to the number that we said at the beginning. The theoretical answer is about 0.0833. However, when we run the simulation, we get the average of the variances is around 0.0746. This is arguably far from where we should be. And the sentence is clearer here. So I'll leave this sentence up for a bit. Since the mean of the variances seem to underestimate the true population variance of 1/12th, our simulation implies that this sample variance is a biased estimator of the population variance sigma squared. In RStudio, we got a value of about 0.07. I probably should have said this at the beginning. What we're doing is, we know in reality, or what's practical, is to do measurements and observations with a relatively small sample of data. We're going to do our calculations there. The main point of today is to see if we could then extend our results and then talk about the much larger population. When is it okay to do that? And then there are times when it's not okay. And those times when it's not okay is because there's a bias in the estimation. So what I did on the RStudio side of things was we calculated some sort of variance, but notice that at the moment I just divided by n. You might remember what we're going to do from here. And it turns out, strangely enough, simply taking the averages of the squared deviations leads to a problem because I'll underestimate sigma squared. That is, there is some sort of systematic bias that will underestimate sigma squared. So go ahead and stretch or however you do to kind of prep yourself because we're going to dive into the really heavy theory now. So the question I'm just kind of asking rhetorically is, can we rescale the process for computing variance so that the operation is an unbiased estimator for the population variance? We're going to once again let the x of i's be a set of NIID random variables, so they have the same distribution and the same population variance sigma squared. And also recall that because the variables are independent, there is going to be zero covariance. And again, what I was doing in the RStudio code was simply taking an average of the square deviation. So we add up all the square deviations, that's what this summation is doing, and dividing by n because that's how many how many observations there were. We saw that this process will underestimate, at least we saw that empirically. And what we're going to do is rescale. We're going to multiply everything by some, at the moment, unknown value of k, so that we would line up the expectation right back with sigma squared. Now, me personally, as a mathematician, I really do like this proof, this calculation. It's a bit clumsy, so sometimes what we mathematicians will do is what we call invoking a lemma. A lemma, if you want to, think of it as kind of a side quest, a side mission. Something that we should do that will help us later. So what's going to happen is we're going to encounter this expression here, the variance of one observation minus x bar. And we're going to need to show that it equals this expression on the right hand side of this equation. When we have a lemma, we mathematicians want to prove the lemma so that we know that it does work out and we are able to use it later. So for starters, recall what x bar is. We simply add up all the random x of i's and divide by n. Now what I want to do is build up towards this expression inside the parentheses, x of I minus x bar. So what I'm going to do with this equation is simply multiply everything by -1 and add an x of I. Well, I say simply, but for the sake of time, I did skip a couple steps here. I assure you that once the algebra is broken down, you'll end up with this coefficient in front of x sub I. And what this last term at the end does is gather up all the terms, such as x1, x2, x3, except for x sub I itself. In other words, we isolated x sub I. Now, what I wanted in the lemma, you could see at the top, is that I wanted to find the variance of this. Thus, the next line in the process is simply slapping the variance operator on all of that. Above, I had said that there is zero covariance, so because of independence, so we don't have to worry about that here. And the capital X's are the random variables, meaning that, say for example, this 1 minus 1 over n, that is a constant with respect to the randomness, and we call that when we factor out a constant from the variance, that constant is squared. And we'll end up with this expression here on the bottom right. At least in my opinion, one thing that always gets me when doing this proof is there's a subtraction sign here, and then a plus sign down here. And that's simply because when the negative 1 over n gets squared, two negatives become positive. So because we had assumed that the x of i's are IID with the same variance sigma squared, all those variances on the right become sigma squared. And from here on out, I'll clean up the algebra a bit. And that's what I wanted from the lemma. I just wanted to grab how to rewrite this particular variance here. I'm about to turn the page in a minute, so I'll stop here for a few seconds to see if there are any more questions from chat. We have about 10 minutes left in our session. The question in chat is, how did this become 1 over n squared? It's the notion that when we factor out a constant from variance, the constant is squared. So now with the lemma out of the way, we'll go back to what I consider the main math problem at hand, is finding the value of k to rescale all this so that we end up with just sigma squared at the end. Finding the value of k so that this whole process will be an unbiased estimator. As a quick side note, for brevity, recall that a horizontal shift does not affect variance. So assume that we've already moved stuff around so that the variables have zero mean. And recall that for our practical formula for variance, e of x squared minus e of x quantity squared, if e of x is 0, that second term after the subtraction sign goes away. And these two notes here are to make the next proof much easier to write. So we're going to run through this, somehow work with this expression on the left-hand side as much as possible. With respect to the randomness, remember the random variables are the capital X's. With respect to the randomness, k and lowercase n are constants, so we could factor those outside of the expectation operator. As usual, the expected value of a sum is the sum of the expected values. So we could switch the sum and a capital E. Now, from this mumbo jumbo that I said above, E of something squared with the assumptions we said before is the same thing as variance. So what goes inside the summation now is variance. And the reason why we did the lemma on the previous page is to handle this particular calculation. So we did that part already. And we got this expression here inside the summation. Now, the summation is done with respect to index I, but you'll notice now there are no i's in this summation. This is a constant with respect to the index. So this is some number added up to itself n times. And then finally, we could solve for k. And thus, this whole hour was to bring us back to the formula that we used at the beginning of the semester, the one where we had the step where we divided by n minus 1. And this is what we call the sample variance. More verbosely, the n minus 1, which in literature is called Bessel's correction, is in place so that the sample variance is an unbiased estimator of the population variance sigma squared. That is to get everything to work out correctly from going from a relatively small sample to the larger population. This is the justification of why we divided by n minus 1. Admittedly, that was a lot to take in. I will have the notes uploaded right after class, but let me just go ahead and finish off this lecture. There are times when we want to talk about standard deviation, and it turns out that sample standard deviation itself is a biased estimator. Similar setup, the X sub i's are IID. They have the same population standard deviation sigma. And just to avoid that troll of a very trivial situation, we're going to assume non-zero variance. That is to say, if all your data had zero variance, that means every single observation was the same number, and it wouldn't be worth studying in a probabilistic sense in the first place. So running through the ideas we encountered today, if the sample standard deviation, which is the square root of the formula we just got above, was an unbiased estimator, then the expected value of that formula, lowercase s, should line us right back up with sigma. However, this is where we bring in that weird idea I presented before spring break. However, by Jensen's inequality, because something squared, a parabola, is a convex function, we actually know that there's an inequality here. So it follows that the expected value of S will be less than sigma by Jensen's inequality. So due to underestimation, we note that in theory, the sample standard deviation S is a biased estimator of the population standard deviation sigma. I have to mention all this for theoretical purposes just to make sure that you have been exposed to these notions so that it doesn't cause you calculation hurdles later in your scientific career. Though I'll admit for this last setting, when we're talking about standard deviations, in practice, the discrepancy is usually so small that it's usually ignored. So it's not a big deal. It's just still theoretically the sample standard deviation is biased in its estimation. All right, thank you all for showing up today. It was good to see you all in this Twitch sense. And I'm going to end the YouTube recording now.